H and D onto the alkene. So I can take an alkene, right, and decide at will to make DH or HD. Now this is important for several reasons. One, normally we use D2 in platinum or H2 in platinum, but that brings HH or DD or TT. This sequence allows you to bring in either an H and a D and a T, an H or a T, and that's good. But what's even better is I can decide where the H and the D go. How would I do that? Well, if I use B2H6, H6, the H goes on the crowded carbon. And then I would use CH3CO2D, which would then replace the boron and go here. But if I wanted to have the D here instead of using B2H6, I'd use B2D6. So the D would come here. And then I would use CH3CO2H, and the H goes there. Suppose I wanted to convert this alkene into this compound. Suppose I wanted a T here and a D here. Well, that's easy. I'm going to use B2T6, right, which would get the T into the crowded side. And then I'm going to use CH3COOD, which would get the D on the other side. Right? So this reaction is really neat because it allows us to make the anti-Markovnikov product, also allows us to put different isotopes of hydrogen on whichever carbon I want at will. I mean, that's the power of organic chemistry. Okay, all right, we've got about 5 more minutes and then we're done. Hydrogen oxidation, right. And just, so again, hydrogen oxidation does anti-Markovnikov, okay? Oh, yeah, I did mention 9-BBN. Let me just say what that is very quickly. 9-BBN is a bicyclic compound. I think this is right. 1, 2, 3, 4, 5, 6, 7, 8, 9, which looks like this. So it's 9-bora bicyclo-nonane. So it's 9-BBN. And one of the reasons this works really well is because it's bulky. So that really gives you a preference, a chemical preference for the boron sticking the H in here and keeping all of this bulk away from whatever group is on that side. So you get a much better yield of your desired product. It's just very expensive. Also, it kind of smells like garlic, and if you're smelling it, you're poisoning yourself because this stuff is really bad for you. Okay, so just 5 more minutes. We'll do something with alkynes, and then we're done. And of course, you guys can pause this lecture as you see fit and come back to it. I don't quite have that luxury, but that's okay. So let's talk about alkynes. And the nice thing with alkynes is alkynes give the same chemistry that alkenes give. They're very much alike. So almost everything we did for alkenes applies to alkynes. So let's talk about one, the preparation of alkenes. You can prepare alkenes A, by elimination, and then B, from, oh wait a minute, okay, that's fine. From lower terminal alkynes. I think we will, that's fine. So if I take this species, say a Vic dibromide, I can treat this with sodamide, and it's usually in mineral oil. So So sodamide in mineral oil and heat, and that's going to give the corresponding alkyne. This is actually a fairly straightforward idea. In fact, if I draw it this way, you'll see what's sort of better what's happening. So it's the HBr and HBr. So essentially what happens is I'm going to lose HBr, I'm going to lose pairs of them. So I'm going to lose HBr and then HBr. Right? I'll do 2 E2 reactions. So the first set, right, the first set of NH2 minus, let's just write it here. So let's imagine I had this, so HBr. The first set of NH2 minus would do this, kick out HBr and generate the corresponding bromoalkene. And then the second H2Br, the second NH2 minus will do another reaction and give rise to the alkyne. So basically you're doing 2 E2 reactions. So I'm going to use 2 equivalents of sodamide to carry the reaction. It works very, very nicely. It turns out it doesn't have to be from the Vic dihalide. I could do the reaction from the gem dihalide. And as you can imagine, right, this would work quite nicely because I eliminate HBr, then HBr. So whether it's with the Vic or the gem doesn't really matter. Now, one interesting point is, when it's the gem, it could have gone with these H's to make the terminal alkyne, or these to make the internal alkyne. They will always make the internal, because internal alkynes are more stable than the terminal alkynes. It's like a tetrasubstituted alkene being more stable than the tri, the di, and so on. So again, these would use 2 equivalents of NH2 minus, in mineral oil and heat. And that's with a gem dibro. There is one little caveat with this reaction, and that is when the alkyne we're making is terminal. For example, if you started off with, say, this compound, if you had this species or this isomer, and you were carrying out the reaction, you have to use 3 equivalents of NH2 minus in mineral oil and heat, followed by water, if your intent was to make the alkyne. Let me just explain why that happens, and then we've got a couple minutes left and we're done. Wow, this is taking longer than I thought. So the immediate obvious difference is that this requires 2, because I'm putting off 2 HBRs, but here it requires 3 and water. So what's happening? And the answer is very, very simple. Let's imagine, it doesn't matter which one I pick, let's imagine I took, let's do that way. Let's say I'm going to use, let's say use the Vic dibromide. And let's say I was silly and I only used 2 equivalents. So let's break it down and say I have 2 molecules of this, right? So 2 equivalents would be 4 NH2 minuses. Okay, so the first NH2 minus will take the first of these molecules into the bromoalkene. Okay, that's one. The second one would take it into the alkyne. Right, so I'll eliminate this HBr and make the alkyne. But here's the problem. Terminal alkynes are acidic enough that the NH2 minus will deprotonate it and make the acetylate. But you've used 3 of the 4 that you've put in. So you have 1 left. That last one is going to do this reaction and then stop. So if you only put in 2 equivalents, you do not make the alkyne. You end up with the acetylate and the bromoalkene. And the thing is, remember, proton transfer is the fastest reaction in organic chemistry. You cannot stop this. If you add hydroxide to HCl, they must react. There's no alternative. If you add NH2 minus to a terminal alkyne, they must react. There's no alternative. So 2 equivalents of NH2 minus will not work. So what do? I'm going to add another NH2 minus. This is extra. So I'm going to write the extra ones in green. This is an extra one, which will give rise to the terminal alkyne. And then I'm going to drive that all the way to with another NH2 minus. So I have a common product, which is the acetylide. I'm going to take the 2 acetylides and just add water to them. And the acetylides will deprotonate water and make your product. So now in all, for the 2 molecules of your substrate, you've added 2, 4, 6 NH2 minuses. That's 3 equivalents. So I must use 3 equivalents to make the acetylide, and then drive the acetylide into the alkyne with water. I would remind you that at this point, I could have chosen to use D2O to make the deuterated species, the 1-deuterio alkyne, or I could have added T2O to make the 1-tritio alkyne. Okay? And then, if you looked at the earlier part of the lecture where we talked about alkenes from lower alkynes, that is the same discussion that we've used to make higher alkynes from lower terminal alkynes, right? So just go back to that bit. All right, so the last thing we do is look at hydration, and then we're done. So under reactions of alkynes, let's do hydrohalogenation. And basically, if I treat, let's make it a terminal one, Markovnikov's rule will apply. If I use, let's say, HBr, the H will go to the carbon having the larger number. So that's going to give me this compound. All right, so I'm going to add HBr followed by HBr. So basically what I would get is HBr, and then as the first HBr, and then the second HBr coming on would give me HBr again. This does the Markovnikov reaction. It is possible to do the reaction under anti-Markovnikov conditions if I use HBr with peroxides. So dialkyl peroxides, what that's going to give you, and we won't go through the mechanism for it, is the isomer, which is the anti-Markovnikov hydrobromination. Just as a note, this works better with Br than with Cl and so on. Okay? So I can hydrohalogenate the alkyne in a Markovnikov sense or in an anti-Markovnikov sense. And then finally, there's hydration. And again, if I take the alkyne, if I treat the alkyne with mercury 2+ in sulfuric acid, I will get Markovnikov, so I should write out this as Markovnikov, and this is anti-Markovnikov, right? I can do the same thing here. I can get Markovnikov, and I can get anti-Markovnikov. So if I use mercury 2+ in sulfuric acid, I'm going to get Markovnikov hydration. Now, here's the thing. When I add H2O across the alkyne in a Markovnikov fashion, what that will give me is H on this carbon and OH on the next carbon. But that gives rise to a very unstable species called an enol. because I've got a hydroxy group on the vinylic carbon, on the alkene. Enols are unstable and undergo a reaction called tautomerization. So it's called keto-enol tautomerization. And what you end up making from this reaction is the corresponding ketone. If I use B2H6 followed by hydrogen peroxide, you've met this reagent set before, that will do anti-Markovnikov, and that's going to give rise to the isomeric enol, which is this one. That will tautomerize to give rise to the corresponding product, which is going to be the aldehyde. So this is also called keto-enol tautomerization. Just 2 quick points before we're finished. So enols are one of the few classes of unstable alcohols that we will meet. It's the only one we meet in Organic 1. Obviously the semester is finished. The tautomerization is an isomerization in which the proton appears to walk across a pi system. So here is the proton at the end of the pi. And what do we mean by pi system? Well, in a sense, if I have this unit, this O has lone pairs. So this is in resonance, right? Like so. And if I were to draw the hybrid, what the hybrid looks like is this. So I can say all of this is part of a pi system. And what appears to happen is the proton walks across from one end of the pi system to that end. So instead of having CH2, I now have CH3. And it looks as if this O went from here to here. Right? So I get a double bond in that position, single bond here, and this H appeared to walk over here. Turns out, in reality, this H is not that H, but mechanistically when we draw it that way. So recognize it's not quite the same. And then if we do anti-Markovnikov, so the OH goes to the other position, right? Then we do keto-enol tautomerization, and we end up with the aldehyde. Oh God, this is the aldehyde. The last point we make is that if you notice, the keto version, and although this is an aldehyde, it's they call keto species. The keto version ordinarily is much more stable than the enol version. Enols are very unstable, in part because the H is unusually acidic and blah, 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 blah. So normally, the keto version predominates. So if I were to take a sample of acetone, and I run the NMR of acetone, I won't see any evidence of the enol. I mean, you just don't see it. The amount of enol is less than a 0.5%. So normally then, the keto version is much more stable unless, and this is interesting, unless there are structural features in the enol that stabilize either the double bond and or the OH group. And there are 2 examples we're responsible for. One example are compounds called beta dicarbonyls. Right, so here's my carbonated carbon, alpha carbon, beta carbon. Beta dicarbonyls are very interesting. They tautomerize, and in the process, and you notice this arrow now is almost 50-50, what they generate is this species. And the reason the enol exists in such large amounts is because the double bond is stabilized by resonance, right? Because I've got a lone pair here, so I can go bang, bang, bang. So I stabilize the double bond in resonance. Okay, I stabilize the double bond in resonance. And I stabilize the OH group by intramolecular hydrogen bonding in a 6-membered ring. Not just any old 6-membered ring, but if you look at the 6-membered ring, it actually has 2, 4, 6 pi electrons in it. So it feels benzene-like, right? And aromaticity is a very strong stabilizing force. So if I were to buy a sample of the beta dicarbonyl, it exists in 50-50 amount roughly to the enol. And the last example, this is where we will stop, is if you have, well, let's put it this way, that compound does not exist, right? Now, this one does exist. Let's see if I have that compound. That compound exists. And for example, if I took that compound, and let's say I eliminated HCl, and let's say my attempt was to do an E2 reaction to make that one, I'll do the reaction, that's not what I'll get. Because this can tautomerize, and when it does, it tautomerizes completely into another enol, which is a phenyl enol or a phenol. This is the stuff they put in the antiseptic spray for your throat. What's it called? Not Listerine. Whatever. The thing is, when you have a sore throat, you spray it in your throat, or you can suck on the lozenges. Phenol kills bugs, kills bacteria, right? So this keto version simply does not exist. It tautomerizes completely into the phenol. And the reason is because the double bond is stabilized in the aromatic ring. So normally when you draw enols, when they're unstable or unstable species, I put them in square brackets. Okay? But in the case of phenol, that's very, very stable, or the enol from the beta dicarbonate, those are pretty stable. Alrighty then, so that's the end of our discussion, and I hope you guys were pausing to get a break along the way, because I know this was a lot altogether. So good luck.